Alright, I've got a riddle for you. Among my siblings I am the thinnest. I am in Paris, but I am not in France. Who am I? Well, if you don't want to know, then just pause the video if you want to think about it. Or just plug your ears so you don't have to hear the lame answer to the riddle. I am the letter I. That's the answer, the letter I. Well, anyway, we're going to try something a little bit different today. I'm going to try the iPad with a PowerPoint and see how that works. See about the quality of that. And anyway, today we're going to start with section 9.4. 9.4, as you can see, is vectors, and you may or may not have ever had a lesson on vectors. Kind of cool. If you've seen the movie Despicable Me, there was a character by the name of Vector. I think it said something like, it fights crime with magnitude and direction. And I actually have that clip, so if you remind me in class, I will show that clip of Vector from Despicable Me. And if you, kind of an interesting timing here, because I think that movie is showing on TV tonight. Anyway, so that's a minute of nonsense here. Just wanted to review what we've done. We have talked about polar. So chapter 9 is all about applying what you've learned from trig. So we've talked about polar. We dealt with the rectangular grid, the polar grid, going from rectangular to polar coordinates, and we talked about the different polar graphs: straight line, diagonal, vertical, and horizontal. And also we had the circles with the center at the origin. You can see the circle there. It's symmetric with respect to the x-axis, and then the one that's symmetrical with respect to the y-axis. And you should know what those equations are. And then we've got, let's see here, we've got the cardioid and the limacons, and we talked about those. And we talked about the rose curves. If the coefficient of the theta is even, then we see that the number of petals of the rose curve is double that, and if the coefficient of the theta is odd, then the number of petals would be the same as that number. So you should be able to graph that equation, 2 plus 2 sine theta. So this is just a quick review of what we've done, and you should have an idea pretty quickly that that would be a cardioid, in which the cardioid is symmetrical with respect to the y-axis. So anyway, let's go ahead and get into vectors. And with vectors, we've got all kinds of fun things we can do. In fact, vectors are used in navigation and in describing things like, probably the most common explanation of a vector would be, let's say we take this airplane, and let's say the airplane is, let me fix my pen here. Let's say the airplane is flying in a certain direction. Okay, so let's say here we have this obviously the airplane is flying in that direction, and then this particular, so that's that vector right there. This vector would describe not only the speed of the airplane, but the direction that the airplane would fly without any wind. Okay, so that's important to understand. Without any wind, that's the direction the airplane is going to fly. Now, the direction of the wind, let's say, is coming from the west and is going out this way. So you have, let's say the airplane is flying at, I don't know, 200 miles an hour, and the wind is blowing from the west towards the east at a speed of, let's say, 100 miles an hour. And then the question would be, well, what direction would the airplane in fact be flying? And the way we answer that is by using vectors. So if we, as we see, we have the two vectors that are, and we'll get into that, tail to tip. The actual direction of the airplane is just like what I'm drawing right there, the actual direction. And so we're going to use vectors to describe things that happen in real life. So if you're into physics, this is probably going to be a pretty easy lesson for you. A couple things to point out that we talk about when we're talking about vectors. We talk about the initial point. So right down here in the lower right-hand part of your screen, we see the initial point of the vector is where the vector starts, and the terminal point of the vector is where the vector ends. Okay, and a couple things that are described here. We have a line containing P and Q, so that's not a vector. And we have a line segment down here that stops at both ends. But then when we have a directed line segment, we can call that a vector, and we use a directed line segment to represent a vector. And a vector has both magnitude, so if we want to think about that, let me write that down. So a vector has both magnitude, and the magnitude would be considered the length of the vector. Okay, and we say that also a vector has direction. Okay, and one thing, I don't really necessarily have room to write this down right here, but what I want you to write down is what a vector is. A vector is a quantity characterized by both magnitude and direction. A quantity, and we use vectors to describe things like the speed and direction of an airplane, speed and direction of the wind that we just talked about. We can use vectors to describe forces, like if you drop a certain object, if it's really heavy, then it's going to have a greater force. You drop it straight down, you can use a vector to describe the force that's being applied, or if you push on something, you can describe the force that's being applied to that. This is all different kinds of things that we can use vectors to describe. And so that's going to take care of the first part of that, just an introduction to vectors. And actually, I say that that's going to be it. But let me go ahead and right in here, I'm going to draw a couple things. If we had a vector that moved up in that direction here, I'm right here, right below the word geometric. If we had a vector like that, we can also move that vector, and as long as another vector has the same direction and the same length, we say that they are the same vectors. Okay. Now a vector that's going straight down, this vector that I just drew straight down is a different vector than the other ones because we see it's in a different direction. It might have the same length. We might have a different length but the same direction. Okay. Different length, same direction, those vectors are not equal. Okay, so the only time two vectors can be equal is when they have the same direction and the same magnitude. Alright, so let's go ahead and stop this now. We'll go on to the